Good morning. This is my first attempt at an online lesson, so bear with me. Hopefully they'll get better as they go along. Today is doing connected particles. I mentioned this in the lesson on Thursday morning. So dealing with forces, this is still going to be using F equals ma. But we're dealing with forces now with particles that are connected to each other. When they're connected to each other, we call them a system. So this first example is going through a system of particles. We have two particles, P and Q, of masses 5 kilograms and 3 kilograms respectively, connected by a light inextensible string, which means that that string will not extend. It's not bungee. It's like a solid thing once it's in tension. Particle P is pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. So first of all, I'm going to draw a picture of this. Here's my rough horizontal plane. That means rough means it experiences friction. I've got my two blocks P and Q. I'll label it above it. That's P and Q. And 5 kilograms and 3 kilograms respectively. Connected by a light inextensible string. P is pulled by a horizontal force of 40 newtons, magnitude 40 newtons. So I'm going to put that this way. That's the 40 newton force forwards. Then we're also told that particle P experiences a frictional force of 10 newtons. So I mark that on here. And particle Q experiences a frictional force of 6 newtons. So that's dragging it backwards. You'll notice in the question it didn't tell us whether it was moving to the right or to the left. We just have to assume using the setup here. It doesn't actually matter whether the whole thing is moving to the right or to the left, as long as the friction is working against the forwards force. The other horizontal forces I need to mark in here are the tension in the string. So Q experiences tension in the string pulling forwards, while P will experience tension pulling backwards. First of all, the first question is to find the acceleration of the particles. So to do this, we treat the system as a whole. There are other forces on here. There's also gravity acting on this one, and of course the normal reaction force acting on both of these as well. But they're going to confuse the diagram, so I'm just going to leave the horizontal forces labeled at the moment. So find the acceleration of the particles. We've got forces, we've got masses, so we just need to put those together to find the acceleration. It's good to label this as something for the whole system that we're working out here. So I'd say whole system, resolving horizontally. Put all of my forces first. Forces to the right being positive. We've only got the forwards force of 40. Working against that is the 10 newtons of friction from P and the 6 newtons of friction from Q. Equals mass. The overall mass of the system is 5 plus 3 kilograms times by the acceleration. So adjusting all of those, that is 24 equals 8a. And dividing both sides by 8, 3 is the acceleration there. So acceleration equals 3 meters per second. Remember to put units in for your answers for part A. Meters per second squared, sorry. I can mark that in here as an arrow this way. The whole thing is accelerating at 3 meters per second squared. And that's going to be useful for me for working out the other things in part B and C. So finding the tension in the string. To do that, I need to isolate this particle Q, or P, but I'm going to choose Q because it has less forces acting on it. So for part B, again, it's important to label what I'm thinking about here. So I'm going to say Q only. So I'm thinking about Q on its own. I'm going to resolve horizontally again. But now that I know the acceleration, I'm going to be able to put that into an F equals ma formula. So forces acting on Q, forwards is T and backwards is 6, equals the mass of Q on its own times by the acceleration of Q on its own. Well, the acceleration of the whole system. So that gives me T minus 6 equals 9. So T equals 9 plus 6, 15 newtons. So that's the tension in the string is 15 newtons. Explaining how the modelling assumptions that the string is light and inextensible have been used, that is something that is given very clearly in the textbook example. So it's to do with the fact that tension is constant throughout the string. So tension is uniform throughout the string. Light and inextensible. Inextensible means it doesn't stretch. Light means it has no mass that's worth considering. So we say it has negligible mass. This is already taking account of Newton's third law, which states that for every action there is an equal and opposite reaction. As in, every time you push something, it pushes back. Every time you pull on something, it pulls back. This is already taking account of this, but we see a even clearer example of that in the second example. So I'm going to move on to the second example, example 12. So here we have a light scale pan is attached to a vertical light inextensible string here. The scale pan carries two masses, A and B. The mass of A is 400 grams, the mass of B is 600 grams. A rests on top of B as shown in the diagram. The scale pan is raised vertically using the string with acceleration 0.5 meters per second squared. So I can add acceleration to this diagram. It's raised vertically, which means it's going upwards. So we have to look for clues in the questions everywhere we can. It's going upwards with acceleration of 0.5 meters per second squared. The reason it's doing that is purely due to the tension in the string, which is pulling it upwards. And it's saying find the tension in the string. For that, we need to consider the system as a whole. So again, whole system. And we're going to do resolving vertically with upwards being positive. And we're going to look for another F equals ma equation. So forces on this, upwards is T, downwards is all of the masses times by gravity. So 400 grams, remember, is the same as 0.4 kilograms. And that's 0.6 kilograms. And we need to think about the weight of the pan. But the weight of the pan is light, as in there's no mass that's worth considering. So a light scale pan means that it has negligible mass, and we're not going to include the mass of the scale pan in our model. So putting those together, the mass of this whole thing is just 1 kilogram. So that is, I'm going to get rid of that bracket actually. Having added them together already, we've got 1 kilogram. That means that we're going to take away 1 times by g, not 1 gram, but 1 times 9.8 acceleration due to gravity. And that is the mass, 1, times by the acceleration, 0.5 meters per second squared. So rearranging that, I'll just do that in a couple of lines. T minus g equals 0.5. I can switch those places. So T minus 0.5. Oh, I already know what g is. It's 9.8. So T equals 0.5 plus g. 0.5 plus 9.8. T equals 10.3 newtons. Tension in the string, 10.3 newtons. And we should give that to two significant figures because we use g as 9.8. So that's why we have in the textbook T equals 10 newtons as our answer for part A. Part B, find the force exerted on mass B by mass A. So we've got mass B sitting here. A is exerting a force on that, and B is exerting a force back. And those forces will be the same. The pressure that A puts on B is exerted back on A by B. So in this, I am going to isolate the thing that has least forces acting on it. So I'm going to say for A only, so this is question B, for A only, I have, so draw a picture of A only. I have its mass times acceleration acting downwards, so that is 0.4 g acting downwards. And then I have the force from B that's making it go upwards, which is what I need to find. So I'm just going to call that R. It's the reaction force from B. And that's making it accelerate upwards at 0.5 meters per second. The system is all accelerating at the same rate. So again, resolving vertically, I have upwards R, force equals mass times acceleration. Forces are R minus 0.4 g. Is the mass, which is A on its own, 0.4, times by the acceleration, 0.5. And that gives me R equals, doing these calculations, 0.4 times 0.5 plus 0.4 times 9.8 gives me 4.12. So again, rounding to two significant figures, this force is 4.1 newtons. And just to clarify, we were asked to find the force exerted on mass B by mass A, this downwards force. We got that by working out the force exerted by B on A, the other way around, the reaction force, because A is easier to treat by itself. And for part C, find the force exerted on mass B by the scale pan. So for this, we can see that A is sitting on B, so the force that's acting downwards on the scale pan, that's the only force that's acting on the scale pan other than the tension in the string. So for this, we're just going to consider the scale pan on its own. So here's the scale pan. It's being pulled upwards by a force T in the string, and the force acting downwards on the scale pan from B, we just call that anything, but the textbook calls it S. It's a downwards force acting on that. Again, so I should put for scale pan only, make it clear what I'm considering in this. And resolving vertically, upwards forces, again I'm looking at a F equals ma equation to set up. So force is upwards force minus the downwards force equals the mass. And the mass of the scale pan is 0, remember, because the scale pan we were told was light scale pan. So there's no mass. Mass times by the acceleration, which we still know is 0.5 upwards. So that leaves us with T minus S equals 0, which means that T equals S. And we know from part A that the tension in the string is 10 newtons, and therefore the pressure acting downwards on the scale pan is also 10 newtons. So force exerted on B. So this question asks for the force exerted on mass B by the scale pan, which is the same as the force exerted by mass B on the scale pan. So force exerted, it's just difficult to get the phrasing right of this, on mass B by the scale pan. So that is a force of 10 newtons, again rounding to two significant figures. That's using the same as from part A. And we need to consider whether this is upwards or downwards. The force exerted on mass B by the scale pan is actually the force acting upwards. So that is 10 newtons upwards for the final answer there. As you're working through the questions in the textbook, just remember that it's all about thinking of the system combined in order to find the acceleration. Most often you'll need to combine the system as a single thing in order to find the acceleration. Once you've got the acceleration, you can separate that into its component parts however you like, but you're always just going to have to consider the what masses are acting on the individual blocks. Think about the contact point. For example, the contact point there has all of A and B acting on it. whereas the contact point there, you would only be considering the effect that A has on B at that point. But if you've got this acceleration that's working the whole way through, you should be able to solve most of the equations. That took a little bit longer than I was expecting, but hopefully it's useful. And I think for this exercise, it really is worth working through every single question. What I'll do for next lesson is post a quiz question on the Google Classroom so that you can answer that there directly. That will be one that doesn't have the answer in the back of the book. So for today you'll see the work I've set is actually the whole exercise, and that should keep you going till Wednesday, which is our next lesson. No, it's not. It's Thursday morning is the next lesson. Okay, take care, stay safe, and I'll be in next time.